SpaceX's Starship project is gathering momentum. A super heavy, reusable rocket capable of lifting up to 150 tons into orbit. A major objective of Starship is to transform human exploration and habitation of space. But along the way, could it also transform our scientific study of the universe? So join us today as we explore the brave new world that might lie ahead for astronomy as we enter the Starship era. It's undeniable that many of the most magnificent images ever captured of the sky are those obtained from space. The now 32-year-old Hubble Space Telescope perhaps best exemplifies this through vistas of stellar nurseries, supernova remnants, and galaxies both near and far. The Earth's atmosphere might be the reason for surface life, but for astronomers, it's a source of constant frustration. Weather, clouds, and dust are common problems, but even in the most quiescent of locations, the movements, swirling, and turbulence of the air distort our view of the heavens above. Astronomers have been launching space telescopes for decades, with the first success being the orbiting Astronomical Observatory 2 in 1968. Nicknamed the Stargazer, its four 12-inch telescopes exploited the fact that they were above the atmosphere to observe in the ultraviolet part of the spectrum, a part which is usually obscured from the ground due to the ozone layer. Since then, dozens of space telescopes have flown, with JWST representing the most famous recent example launching just last year. Yet despite decades of experience and the undeniable benefits of having a space telescope, they remain a relatively precious resource, greatly outnumbered by their ground-based cousins. Today, there's a lot of excitement about the potential for a shakeup of this status quo though. Since 2015, SpaceX have been successfully recovering the first stage of their Falcon 9 rocket through the, quite frankly, breathtaking achievement of landing them vertically back on the Earth. Remarkably, this has become somewhat routine at this point, with approximately 100 successful recoveries to date, now extending to the fairings and side boosters of the Falcon Heavy too. And it's not just SpaceX. Many others see reusability as our future, such as Blue Origin and ESA. The real point of all of this is to reduce costs. If you can recover and reuse your spacecraft, then expenses will fall and ultimately become limited by the price of your fuel alone. And indeed, this strategy is clearly working, with prices plummeting. To get into low Earth orbit, the expendable Atlas V rocket operated by ULA charges as low as $8,100 per kilogram, going north of that for other configurations. Now in comparison, the Falcon 9 reusable rocket by SpaceX currently comes in at about $4,100 per kilogram, so that's almost half the cost. Besides from reusability, the tonnage of the launcher also matters. Heavy launchers can generally reduce the cost per kilogram through their sheer size. Whereas the Falcon 9 can put 16 tons into orbit, the Falcon Heavy can put 85% more up for just 45% more cost. And that means that low Earth orbit launch costs drop to just $3,200 per kilogram, or $1,500 per pound. Now, clearly, these lower costs will benefit anybody wishing to launch something into space, which includes astronomers. In 2018, NASA's TESS mission launched on board a Falcon 9 at a cost of $87 million. TESS is one of the space observatories that we here in my team are currently using, a telescope designed to search for transiting planets around nearby stars. Now, the actual spacecraft cost $200 million, so that means that the total upfront costs were $287 million, of which 30% was simply the launch cost alone. And that brings up our first big advantage. Cheaper launch costs lead to cheaper missions. And so that means that NASA will have more money left over to upgrade their hardware, hire more scientists, or supply more research funding to each of their missions, each of which will improve the science yield of these endeavors. So going to rockets even bigger than the Falcon Heavy could make the price per kilogram even cheaper, and this is of course where Starship comes in. So let's just quickly cover what this rocket even is. Starship is SpaceX's planned super heavy launcher, which means that it can lift more than 50 tons into orbit. In fact, it actually aims to launch up to 150 tons. The concept was first outlined in 2005 when SpaceX CEO Elon Musk called it BFR, the Big Falcon Rocket. Its ultimate purpose was described as ferrying people to Mars, aiming to ship 100 passengers per flight, but would of course be capable of lifting satellites, lunar missions, and be fully reusable. The design has since been renamed Starship, a two-stage system coming in at over 120 meters in height. That's about the same as a 35-story building. Confusingly, the upper stage is known as Starship, but also the entire rocket itself, including the booster, is also known as Starship. And it has to be said that the name is somewhat misleading because, let's face it, Starship is not capable of flying to another star, at least not in human lifetimes, but hey, it's good branding. But regardless, Starship would be a giant, towering over both the Saturn V rocket used during the Apollo missions, as well as NASA's own Super Heavy rocket under development, known as SLS. Starship expects to be able to lift approximately 150 tons into low Earth orbit, which is truly enormous. For context, the now demised Mir space station weighed about 130 tons, meaning that Starship could lift an entire space station up in a single flight. But going further, the real plan is to refuel the ship in orbit, using a second Starship variant known as Tanker Starship. After this fill-up, Starship would have enough fuel to carry 40 tons to a lunar orbit, or even the full 150 tons if it was able to refuel a second time at the moon itself. Another option is to carry less but go faster, and Starship here could play an important role for deep space exploration. In principle, Starship could get around the solar system quicker, since it won't need to meander around looking for multiple gravity assists to get up to speed. Instead, it can just fire its powerful Raptor rocket. And although in this video we're primarily interested in astronomy applications, it has to be said that Starship will open up some incredibly exciting opportunities for planetary science and solar system exploration as well. For context, the Saturn orbiter mission, Cassini, was the heaviest deep space probe ever launched at 5.6 tons. The upcoming Europa Clipper mission will slightly beat that out at just over 6 tons. But all of this kind of pales into insignificance when you consider that Elon Musk said in a meeting with the National Academy of Sciences last year that Starship could transport 100 tons to Europa. 100 tons. Such a feat would be truly revolutionary for solar system exploration. It would open up radical new opportunities. But even without the radical, Uranus was recently identified as the top priority for an upcoming NASA flagship mission in the recent Planetary Decadal Survey, and so Starship would be the obvious potential launch vehicle. And it's not just the mass, the interior volume of Starship is huge, approaching 1,000 cubic meters in some configurations. This is enabled by its 9-meter diameter and up to 22 meters of interior height in the extended payload version. This means that for both planetary science missions and space telescopes, engineers have to spend far less time and money trying to fold their precious equipment into nuanced shapes just to fit inside the rocket. Indeed, a mission to Mars could plausibly load up a full-sized drilling rig, one capable of not just scratching the Martian surface but tunneling up to a kilometer down into the surface. JWST perhaps best exemplifies the potential benefits of this increased volume. Its 6.5 meter mirror had to be built in a segmented design in order to fit inside the Ariane 5 spacefaring, which is just 5.4 meters. But the problem is that multiple mirrors can't be simply added together to create a crisp image. They require precise alignment, which meant that they need to be equipped with precision actuators and several weeks of alignment calibration. That was a process that began on January 12th and only finished on February 25th. But for Starship, a 6.5 meter single monolithic mirror would have easily fit inside, which would have saved enormous costs on the segmentation design and testing, and provided astronomers with many additional weeks of observing time. By leveraging Starship's increased volume, JWST could use fewer foldings, reducing the complexity and thus improving the overall reliability. JWST notoriously had 344 single points of failure at launch, all of which demanded a lot of testing, overruns, and extra expense. No wonder then that the final cost was about $10 billion. It's probably fair to wonder at this point just how is Starship pulling this off, and is this just a pipe dream or something actually close to flying soon? Well, to start with, there are lots of differences between Starship and the previous Falcon rockets. In fact, that's probably why they changed the name from BFR to Starship, because ultimately this rocket shares far less heritage than Falcon Heavy did with Falcon 9. There are two big differences to highlight between these launchers. One is the engines, and the second is the materials. So first, rather than use the Merlin engines of the Falcon 9, which used RP-1 kerosene and liquid oxygen, often dubbed Kerolox, Starship will use the new Raptor engine, which uses methane plus liquid oxygen, or Methalox. You might expect hydrogen to be the fuel here, but SpaceX have long avoided hydrogen despite its greater specific impulse. And that's because it requires extreme cooling, embrittlement protection, added complexity, and added insulation weight. RP-1 kerosene has a good track record as an alternative, being used by Soyuz, Delta, Atlas, and Antares rockets, for example, so it made sense to start there during SpaceX's early days. However, the soot produced by RP-1 combustion makes the tanks difficult to reuse, requiring significant refurbishment between each launch. This is one of the chief reasons why we see the switch to methane now, which leaves no such soot, just carbon dioxide and water. Now, methane is less dense than kerosene, but because of the cleaner burn, it's possible to get very high efficiencies out of it. This is especially true when combined with a full flow stage combustion design, which uses pre-burners to heat up the oxygen and fuel before entering the combustion chamber, thus further improving the efficiency. But perhaps the most striking difference is the visual appearance of Starship, a glistening metallic tower. Whereas Falcon 9 took a fairly traditional approach of using aluminium alloy and carbon composites, Starship uses stainless steel 304L. Now, aluminium is lighter and thus might seem preferable, but because Starship aims to be fully reusable, the material has to survive both cryogenic temperatures pre-launch and extremely high temperatures during re-entry. Stainless steel is strong enough that the booster won't require any additional heat shielding at all. Now, another good option here would be carbon fiber, but SpaceX ultimately opted for stainless steel because it's simply far easier and cheaper to construct, modify, and prototype designs. And this really highlights the key philosophy of Starship and indeed SpaceX: trial by error. Whereas traditional NASA philosophy would be to calculate everything to the nth degree before launching, SpaceX have a history of just trying stuff, which often initially doesn't work. They learn through empirical failures and constant iteration. This is exemplified by the fact that already 4 Starships have been blown up in high-altitude test flights, each of which is merely considered a learning opportunity for the company. Manifestly, this philosophy has been bringing down costs, allowing them to try previously unthinkable things like landing a booster back to the Earth. They also have a highly vertically integrated organization and can accomplish almost everything they need in-house. This is obviously radically different from NASA's organization and approach. Indeed, recently there has been a lot of critical attention comparing Starship with NASA's own SLS system, which is a similar sized, super heavy launcher which is currently under development. To date, NASA has spent a staggering $23 billion on SLS without any flights, despite originally aiming for late 2016. In a recent House Science Committee hearing, NASA Inspector General Paul Martin stated that each SLS rocket would cost $2.2 billion to build. Now, when comparing to Starship, well, let's just listen to what SpaceX CEO Elon Musk had to say about that in February this year.
But I'm highly confident it would be less than $10 million all in over, if you say like fast forward like 2 or 3 years from now.
Even if this estimate is too low by, let's say, a factor of 10, Starship would still be 22 times cheaper than the similar-sized SLS system. Yet more, with its reusability and refuelability, Starship could carry a whopping 150 tons to the moon versus just 43 tons with the SLS system. SLS is aiming for their first maiden flight by August this year, whereas for Starship, things are less clear. In February, Musk stated that it would happen by the end of the year, and in March he predicted by May. But the FAA has delayed their environmental assessment report, and there's the possibility they may need to shift from Texas at Starbase to the Kennedy Space Center in Florida, where the Falcons and Heavy Falcons currently launch from. Nevertheless, a prototype named SN-15 successfully flew for 6 minutes up to 10 kilometers altitude and then safely landed in May last year. Orbital tests will hopefully follow, but undoubtedly again with more explosions along the way. That's just how SpaceX do it. But development seems on track given their past history. So it may be a couple of years before astronomers or really anyone else can launch payloads using Starship into orbit. But in the meantime, perhaps it's not unreasonable that we can dream up what kind of new opportunities Starship might present for astronomers. As already alluded to, one clear benefit of Starship would be cheaper missions, being driven by 3 different effects: reduced launch cost, reduced spacecraft complexity, and heavier payloads. The cheaper launch cost is straightforward enough, bringing down what has historically been a significant portion of a space telescope's budget. Just look at the TESS mission, for example. However, I think the real opportunity is the reduced complexity that flagship missions could get away with, thanks to the large interior volume on board. As we've already covered, JWST saw a lot of added complexity to accommodate the dimensions of the Ariane 5 fairing, and that complexity adds engineering costs, testing expenses, higher risk, and lost calibration time. The ability to launch heavier masses into space raises some interesting cost-saving possibilities too, because typically optical mirrors on space telescopes are specially fabricated to be ultra-light, largely because of historical launch limitations. For example, both the Kepler and Hubble Space Telescope mirrors are made of ULE glass with 2 thin sheets supported by ribs in the center. You can actually see an example of this in the uncoated backup mirror of Hubble, which is found in the Smithsonian Air and Space Museum. This design significantly reduces the mass. For example, Kepler's primary mirror is 14% the weight of a solid structure. But if the launch cost per kilogram continues to slide down, it may become cheaper to simply repurpose existing mirrors on ground-based telescopes for space. Starship could thus potentially enable large, heavy glass mirrors to be launched much more easily, perhaps leading to a fleet of JWST-sized telescopes for astronomers. In such a scenario, it may be possible to have bespoke flagship missions. Now, as a counterexample, the Hubble Space Telescope and JWST are not that. They are general-purpose observatories that serve cosmologists, exoplanetary scientists, and stellar astrophysicists. And so each of those groups has their own needs and desires that affects the design, and so ultimately you end up with something that doesn't really satisfy anybody perfectly, but serves everybody reasonably well. A bespoke mission, such as Kepler, is able to hone its design completely around a singular goal, and that was ultimately a large part of its success. So one possibility is scaling up such telescopes to larger sizes. But another option is to launch constellations of them. The Nautilus project led by Daniel Apai gives a possible example of this, where they plan to launch 15 8-meter class telescopes all at once with Starship. These mass-manufactured telescopes aim to be scalable and cheap, using an innovative diffractive lens system. Together, the fleet can point at different stars or combine together and point at just one, providing a total effective telescope size of 50 meters in space. And concepts like Nautilus really hint at what's most exciting here, because Starship allows us to be truly ambitious, to try things dramatically new, things which have never been done before. One possibility is to piggyback off the Artemis moon program and use it to send telescopes to the moon. Liquid mirror designs could exploit the low gravity to have enormous mirrors of order of 100 meters, yet all whilst enjoying vistas of the cosmos unimpeded by any atmosphere. Going further, the lunar far side represents somewhat of a holy grail for radio astronomers, an extraordinarily quiet location to detect the gentle humming of the universe, as well as the best place in the inner solar system to listen for alien communications. Starship would also make the Lagrange points more accessible, one of the best places to position space telescopes. For example, one ambitious idea that we're working on here in the Cool Worlds Lab is the idea of positioning a small telescope plus large occulter along the refractive focal line caused by the Earth's atmosphere, allowing one to possibly turn the entire planet into a giant telescope lens of unprecedented size, a concept we call the terrascope. You can even do the reverse and turn planets into gigantic antennae, allowing one to potentially connect much of the solar system together through high data volume radio connections, the first system-wide internet. Who's ready for 4K video streams from Europa? So we have cost and ambition, but Starship begets one final opportunity for astronomers: an appetite for risk. Perhaps the philosophy of SpaceX to build, fail, learn, and try again holds a potent lesson for astronomers too. By analogy, JWST is our SLS, a NASA flagship project that was massively delayed and that went ludicrously over budget. And I think there's a good argument that we need to relax this conservative mindset and look for ways to mirror the successes of SpaceX in future astronomy endeavors, to embrace new ideas and concepts, to adopt an iterative empirical approach to future mission design, and to learn to tolerate the inevitable greater level of risk that comes with that approach. After all, nothing ventured, nothing gained. So, until next time, stay thoughtful and stay curious. Thank you so much for watching, everybody. If you enjoyed this video, be sure to do all the YouTube things, like, share, subscribe, comment, and if you want to take your support to the next level, then you can become a donor to my research team here at Columbia University, the Cool Worlds Lab, by using the link up above. So until next time, see you around the galaxy.